The story of the universe is the story of us. From the fiery birth of the Big Bang to the formation of stars, planets, and life, every moment of cosmic history has led to this one. You, here, now, listening to the tale of eons. The atoms in your body were forged in ancient stars, your existence a product of billions of years of cosmic evolution. As we stand on this small blue planet, orbiting an ordinary star in an ordinary galaxy, we are part of something extraordinary. A universe that is vast, dynamic, and full of wonder. This journey, from the first flash of creation to the distant future, reveals our dual nature, insignificant in the cosmic scale, yet profound in our ability to understand it. We are the universe reflecting on itself, a fleeting spark of consciousness in an eternity of existence. The questions we ask: how did it begin? Are we alone? What comes next? Drive us to explore, to build telescopes, to launch probes, to dream of worlds beyond our own. Our story begins nearly 13.8 billion years ago, in a moment so profound it defies comprehension. There was no space, no time, no matter, only a singularity, a point of infinite density and infinite potential. Then, in a fraction of a second, everything changed. The Big Bang, a cosmic explosion of unimaginable power, marked the birth of the universe. This wasn't an explosion into space, but an expansion of space itself, a sudden unfurling of reality that set the stage for everything that would follow. In the first trillionth of a second, the universe grew from smaller than an atom to larger than a galaxy, a process called inflation that smoothed out the cosmos and laid the foundation for its structure. In those earliest moments, the universe was a seething cauldron of energy, hotter than a billion suns, denser than anything we can imagine. The fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, were unified, indistinguishable in the primal chaos. As the universe expanded and cooled, these forces began to separate, like notes emerging from a single chord. Within a microsecond, quarks and gluons, the building blocks of matter, formed in a frenetic dance of creation. These particles, governed by the strange rules of quantum mechanics, collided and combined, setting the stage for the first atoms. The Big Bang wasn't a single event. It was a process, unfolding over fractions of a second that shaped the cosmos forever. By 1 second after the Big Bang, the universe had cooled enough for protons and neutrons to form, the seeds of atomic nuclei. Yet, it was still too hot for atoms to hold together, a plasma of charged particles bathed in blinding light. This was the cosmic microwave background, the faint echo of creation that we can still detect today, a snapshot of the universe's infancy. The early universe was a place of extremes, a realm where the laws of physics were tested to their limits. Theories like quantum field theory and general relativity, developed billions of years later by human minds, help us piece together these first moments. Scientists like Alan Guth, who proposed inflation in 1980, and George Gamow, who predicted the cosmic microwave background in 1948, gave us the tools to understand this cosmic dawn. Yet, mysteries remain. What triggered the Big Bang? Was there a before? And why did the universe emerge with just the right conditions for stars, planets, and life? The Big Bang set the universe in motion, but it was only the beginning. As the cosmos expanded, it began to cool, allowing the first building blocks of matter to take shape. This transition, from pure energy to the seeds of structure, was a pivotal moment in cosmic history. As we move forward, we'll explore how these particles coalesced, how light emerged from darkness, and how the universe began to take on the form we recognize today. As the universe aged beyond its first second, it entered a new phase, one where the chaos of creation began to give way to order. By 3 minutes after the Big Bang, the universe had cooled to about 1 billion degrees Kelvin, still hotter than the core of a star, but cool enough for protons and neutrons to combine into the first atomic nuclei. This process, called Big Bang nucleosynthesis, produced hydrogen, helium, and trace amounts of lithium, the elements that would one day form stars and galaxies. About 75% of the universe's matter was hydrogen, 25% helium, a ratio that still holds today. For the next 380,000 years, the universe remained a dense, opaque plasma, a sea of charged particles where light could not travel far. Electrons zipped freely, scattering photons in a cosmic fog. Then, a turning point. The universe cooled to about 3,000 degrees Kelvin, allowing electrons to bind with nuclei to form neutral atoms. This era, known as recombination, marked the moment when the universe became transparent. Light was free to travel, creating the cosmic microwave background, a faint glow that fills the cosmos and serves as a relic of this ancient time. The cosmic microwave background, discovered by accident in 1965 by Arno Penzias and Robert Wilson, is one of our greatest windows into the early universe. Their radio telescope detected a faint hiss, a signal that turned out to be the cooled remnant of the Big Bang's light, now stretched to microwave wavelengths by the universe's expansion. Later experiments, like the Cosmic Background Explorer in 1989 and the Planck satellite in 2008, mapped this light in exquisite detail, revealing tiny fluctuations that would grow into the galaxies we see today. These fluctuations, or density variations, were the seeds of structure. In regions slightly denser than their surroundings, gravity began to pull matter together, setting the stage for the formation of stars and galaxies. This was a slow process, taking millions of years, as the universe continued to expand and cool. The interplay of gravity and expansion shaped the cosmos, creating a delicate balance that allowed structure to emerge without collapsing into chaos. The formation of matter and light was a turning point, a moment when the universe transitioned from a formless plasma to a cosmos with the potential for complexity. It was the foundation for everything that followed: stars, planets, and eventually life. As we move into the next segment, we'll see how these seeds of structure grew into the first stars, igniting the darkness and transforming the universe forever. By about 100 million years after the Big Bang, the universe was ready for its next act. The cosmic fog had cleared, and the seeds of structure, those tiny density fluctuations in the cosmic microwave background, began to grow under gravity's pull. Clouds of hydrogen and helium gas, vast and diffuse, started to collapse, their particles drawing closer until they reached a critical point. Then, in a burst of light, the first stars were born, igniting the cosmic dark ages and ushering in a new era of the universe. These first stars, known as population 3 stars, were unlike anything we see today. They were massive, hundreds of times larger than our sun, and composed almost entirely of hydrogen and helium. Their intense gravity and heat triggered nuclear fusion, fusing hydrogen into helium and releasing tremendous energy as light. These stars burned hot and fast, living only a few million years before exploding as supernovae, scattering heavier elements like carbon, oxygen, and iron into the cosmos. These elements, forged in the hearts of stars, would become the building blocks of future stars, planets, and life. The birth of stars didn't happen in isolation. As gravity pulled matter together, stars clustered into the first galaxies, small, irregular collections of gas, dust, and light. These proto-galaxies, some forming as early as 200 million years after the Big Bang, were the ancestors of the Milky Way and other modern galaxies. Observations from telescopes like Hubble and the James Webb Space Telescope, launched in 2021, have revealed these ancient galaxies, faint smudges of light from a time when the universe was young. The formation of galaxies was a chaotic process, driven by gravity and shaped by collisions. Early galaxies merged, grew, and evolved, forming the spiral and elliptical shapes we see today. At their centers, supermassive black holes began to form, their immense gravity pulling in gas and stars, powering bright quasars that outshone entire galaxies. These black holes, some with masses billions of times that of the Sun, remain a mystery. How did they grow so large, so quickly? The birth of stars and galaxies transformed the universe. The light from these first stars ionized the surrounding gas, ending the cosmic dark ages in a process called rionization. By 1 billion years after the Big Bang, the universe was a vibrant place, filled with glowing stars, swirling galaxies, and the seeds of future worlds. This era set the stage for the next chapter of cosmic evolution, as we'll explore in the next act, the rise of planets, solar systems, and the conditions that would one day give rise to life. With the birth of the first stars and galaxies, the universe entered a new phase, the stellar epoch, a time when stars became the engines of cosmic evolution. Over billions of years, these celestial furnaces forged the elements that make up our world, from the carbon in our bodies to the iron in our blood. This was an era of creation and destruction, where stars lived and died, shaping the cosmos with their light and their explosive ends. The first stars, those massive population 3 giants, burned brightly but briefly, exploding as supernovae within a few million years. These explosions were cataclysmic, scattering heavier elements, carbon, oxygen, nitrogen, and more, into the surrounding space. These elements enriched the interstellar medium, the gas and dust between stars, providing the raw materials for the next generation of stars. These second-generation stars, known as Population 2, were smaller and longer-lived, some still shining today in the oldest parts of our galaxy. As galaxies grew, so did the complexity of star formation. In regions dense with gas, new stars were born in clusters, their light illuminating vast nebulae. The Orion Nebula, visible today in our Milky Way, is a stellar nursery where stars are still forming, a reminder of the processes that began billions of years ago. Gravity orchestrated this cosmic ballet, pulling gas into dense cores, igniting fusion, and creating stars of all sizes, from red dwarfs that burn for trillions of years to blue giants that blaze and fade in mere millions. Supernovae played a crucial role, not just in creating elements but in triggering new star formation. The shock waves from these explosions compressed nearby gas clouds, sparking the birth of new stars. This cycle of birth and death drove the chemical evolution of the universe, increasing the abundance of heavier elements, or metals, in astronomical terms. By a few billion years after the Big Bang, the universe was rich enough in these elements to form rocky planets, a critical step toward life. Galaxies also evolved during this epoch. Mergers between galaxies created larger, more complex structures, like the spiral arms of the Milky Way or the elliptical shapes of massive galaxy clusters. At the heart of many galaxies, supermassive black holes grew, feeding on gas and stars, their accretion disks glowing as quasars and active galactic nuclei. These cosmic powerhouses influenced galaxy formation, regulating star birth and shaping the distribution of matter. The stellar epoch was a time of transformation, when the universe went from a simple mix of hydrogen and helium to a cosmos rich with diversity. Stars became the alchemists of the universe, turning primordial elements into the building blocks of planets and life. As we move forward, we'll explore how these elements came together to form solar systems, setting the stage for worlds like our own. About 4.6 billion years ago, in a spiral arm of the Milky Way, a cloud of gas and dust began to collapse. This cloud, enriched with elements from ancient supernovae, swirled and condensed, giving birth to a star, our Sun, and a disk of material that would become the planets, moons, and asteroids of our solar system. This process, repeated countless times across the universe, marked the rise of planetary systems, the next chapter in cosmic evolution. The formation of planets begins with a protostellar disk, a flattened ring of gas and dust orbiting a young star. Within this disk, particles collide and stick together, forming planetesimals, small rocky bodies that grow through accretion. Over millions of years, these planetesimals merge to form planets, from gas giants like Jupiter to rocky worlds like Earth. This process, observed in distant star systems through telescopes like ALMA, the Atacama Large Millimeter Array, is a universal one, happening wherever stars are born. Our solar system is a case study in this process. The Sun formed first, its gravity pulling in most of the cloud's mass. The remaining material sorted itself by distance and temperature. Rocky planets like Earth and Mars formed closer to the Sun, where it was too hot for gases to condense, while gas giants like Jupiter and Saturn formed farther out, where ices and gases could accumulate. Smaller bodies like asteroids and comets remained as leftovers, relics of the solar system's chaotic youth. The early solar system was a violent place. Impacts were common, as planetesimals collided and planets grew. Earth's moon likely formed from such a collision when a Mars-sized body struck the young Earth, ejecting debris that coalesced into our lunar companion. This giant impact hypothesis, supported by lunar samples from the Apollo missions, highlights the dynamic nature of planet formation. Beyond our solar system, the discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding. Since the first confirmed exoplanet in 1995, over 5,000 have been found, ranging from gas giants to Earth-like worlds. Telescopes like Kepler and TESS have revealed that planets are common, with many stars hosting entire systems. Some, like those in the TRAPPIST-1 system, orbit in the habitable zone, where liquid water could exist, raising the possibility of life elsewhere. The rise of planets and solar systems marked a turning point. The universe, once a realm of stars and gas, now had worlds, places where the conditions for life could emerge. As we move into the next segment, we'll explore how these conditions led to the most remarkable phenomenon of all: the emergence of life on at least one small blue planet. About 3.8 billion years ago, on a young, turbulent Earth, something extraordinary happened. Life emerged. From the chemical soup of Earth's oceans, simple molecules combined, forming the first self-replicating systems, the seeds of biology. This moment, known as abiogenesis, marked the transition from a universe of matter and energy to one capable of hosting life, consciousness, and curiosity. How did this happen, and could it have happened elsewhere? Earth's early environment was harsh, volcanic, bombarded by meteors, and bathed in ultraviolet radiation. Yet, it had the ingredients for life: water, organic molecules, and energy from lightning, heat, or sunlight. In places like deep-sea hydrothermal vents or shallow tidal pools, these ingredients came together. Experiments like the 1952 Miller-Urey experiment showed that simple molecules, like amino acids, could form under early Earth conditions, suggesting a pathway from chemistry to biology. The first life forms were likely simple, single-celled organisms, similar to modern bacteria. They lacked nuclei or complex structures, but were capable of metabolism and replication. Over hundreds of millions of years, these microbes evolved, developing photosynthesis, which released oxygen into the atmosphere. This great oxygenation event, around 2.4 billion years ago, transformed Earth, paving the way for more complex life. By 600 million years ago, multicellular organisms appeared, leading to the Cambrian explosion, a rapid diversification of life around 540 million years ago. Fossils from this period, found in sites like the Burgess Shale, show an explosion of forms, creatures with shells, spines, and limbs, the ancestors of modern animals. Over time, life spread from oceans to land, giving rise to plants, insects, dinosaurs, and eventually mammals. The story of life on Earth raises a profound question: is it unique? The discovery of extremophiles, organisms thriving in Earth's harshest environments, like acidic springs or deep-sea vents, suggests life is resilient. On Mars, evidence of ancient water and organic molecules hints at past habitability. Jupiter's moon, Europa with its subsurface ocean, and Saturn's moon Enceladus with its water plumes are prime targets for astrobiology. The search for life beyond Earth, driven by missions like NASA's Perseverance rover and the upcoming Europa Clipper, is one of science's greatest quests. Life's emergence on Earth was a cosmic milestone, a moment when the universe became aware of itself. It set the stage for intelligence, culture, and the ability to look back at the stars and ask how it all began. As we move into the modern era, we'll explore how the universe has continued to evolve and how humanity is unraveling its deepest mysteries. Today, the universe is a vast, intricate tapestry of galaxies, each containing billions of stars and planets. About 1 billion years after the Big Bang, galaxies began to form the large-scale structure we see today. Clusters, superclusters, and vast walls of galaxies separated by cosmic voids. The Milky Way, our home, is one of hundreds of billions of galaxies, a spiral galaxy 100,000 light-years across, containing some 200 billion stars. This structure is shaped by gravity, but another force has emerged as a dominant player: dark energy. Discovered in 1998 through observations of distant supernova, dark energy is a mysterious force driving the universe's expansion to accelerate. Unlike gravity, which pulls matter together, dark energy pushes it apart, stretching space itself. It makes up about 68% of the universe's energy, with dark matter, another enigma, accounting for 27%, and ordinary matter just 5%. Dark matter, invisible but detectable through its gravitational effects, holds galaxies together and shapes their formation. Without it, the Milky Way would fly apart. Observations of galaxy rotation curves and gravitational lensing, like those from the Hubble Space Telescope, confirm its presence, but its nature remains unknown. Is it a new particle? A flaw in our understanding of gravity? The answer eludes us. The interplay of dark matter and dark energy has sculpted the modern universe. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies bound by gravity, while dark energy drives them apart on larger scales. The cosmic web, filaments, walls, and voids, emerges from this tug-of-war, a structure mapped by surveys like the Sloan Digital Sky Survey. The age of galaxies is also an age of diversity. Some galaxies are active, powered by supermassive black holes that emit jets of radiation. Others are quiet, like the Milky Way, steadily forming stars. Telescopes like the James Webb Space Telescope have revealed galaxies from the universe's infancy, offering clues to how they formed and evolved. As we look out, we look back in time, seeing the universe as it was billions of years ago. The discovery of dark energy has reshaped our understanding, suggesting a universe that will expand forever. But it also raises questions about what we can't see, about the forces and mysteries that still define our cosmos. As we move forward, we'll explore how humanity has sought to unravel these mysteries, bringing the universe into focus. For millennia, humans have looked to the stars, seeking answers to the universe's greatest questions. Ancient astronomers like Ptolemy and Copernicus mapped the heavens, laying the groundwork for modern cosmology. By the 20th century, new tools, telescopes, spectroscopy, and particle accelerators transformed our understanding, turning myths into science. Edwin Hubble's 1929 discovery that galaxies are moving away from each other confirmed the universe's expansion, a key piece of the Big Bang model. Albert Einstein's theory of general relativity, published in 1915, provided the mathematical framework, describing gravity as the curvature of space-time. These breakthroughs, combined with observations from telescopes like Mount Wilson and Palomar, revealed a dynamic, evolving universe. The space age, beginning with Sputnik in 1957, opened new frontiers. The Apollo missions brought humans to the moon, while robotic probes like Voyager explored the outer solar system. Telescopes like Hubble, launched in 1990, and Chandra, launched in 1999, captured images of distant galaxies, nebulae, and black holes, revealing the universe's beauty and complexity. Particle physics has also played a role. Experiments at CERN, using the Large Hadron Collider, have probed the fundamental particles and forces that govern the early universe. The discovery of the Higgs boson in 2012 confirmed a key piece of the Standard Model, helping us understand how matter gained mass after the Big Bang. Today, missions like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory are pushing the boundaries further, mapping the early universe and searching for exoplanets. The search for life, driven by astrobiology, explores Mars, Europa, and beyond, while SETI listens for signals from intelligent civilizations. These efforts, combined with theoretical advances, bring us closer to answering questions about the universe's origin, structure, and fate. Humanity's quest is not just scientific, it's philosophical. We seek to understand our place in the cosmos, to know whether we're alone, and to grasp the meaning of our existence. As we move into our final segment, we'll look to the future, exploring where the universe is headed and what it means for us. The universe is not static, it's expanding, evolving, and headed toward an uncertain future. Current observations suggest that dark energy will continue to drive the universe's expansion, accelerating galaxies away from each other. In 1 trillion years, the night sky will be nearly empty, as most galaxies move beyond our observable horizon. Stars will burn out, their fuel exhausted, leaving behind white dwarfs, neutron stars, and black holes. In the far future, the universe may face one of several fates. The Big Freeze scenario, supported by dark energy's dominance, predicts a cold, dark cosmos where entropy reigns and all energy dissipates. Alternatively, if dark energy behaves differently, the universe could collapse in a big crunch, returning to a singularity. Or, in the Big Rip, dark energy could tear apart galaxies, stars, and even atoms. These scenarios, while speculative, are grounded in our understanding of cosmology. Yet the future is not just about endings. Humanity, or whatever intelligence follows, may find ways to survive, harnessing energy from black holes or migrating to new regions of the cosmos. Projects like Elon Musk's SpaceX and NASA's Artemis program aim to make humanity multi-planetary, a first step toward a cosmic future. Theoretical ideas, like wormholes or faster-than-light travel, remain speculative but inspire us to dream of exploring beyond our current limits. The universe's future also raises questions about life and intelligence. If life exists elsewhere, will we encounter it? The Fermi paradox, why haven't we seen signs of intelligent life, suggests possibilities. Life may be rare, civilization short-lived, or advanced beings hidden from us. The search continues, driven by hope and curiosity. The story of the universe is ongoing, and we are part of it. Our discoveries, from the Big Bang to dark energy, have revealed a cosmos of staggering complexity and beauty. As we look to the future, we carry the legacy of eons, a universe that has given rise to stars, planets, and us. Let's move to our epilogue, where we'll reflect on what this story means for humanity. The future of the universe may be uncertain, but our role in it is not. We are explorers, storytellers, and seekers of truth. Whether we find life on Mars, signals from distant stars, or simply more questions, the search itself is what defines us. The universe has given us the gift of existence, and in return, we give it meaning through our curiosity, our discoveries, and our stories. Thank you for joining us on this epic voyage through eons of existence. If you've been inspired by this story, please like, subscribe, and share your thoughts in the comments. What does the universe mean to you? How will we shape its future? Let's keep the conversation going. Until next time, keep looking up, keep questioning, and keep marveling at the cosmos that made us. The universe is vast, and our story within it is just beginning.